These are actually
That's a good idea. All right, let's get started. Hello everyone, welcome to the second lecture. Let me start by a couple of announcements. So the first one is that we need 2 people to scribe for today's lecture.
Yeah.
All right, perfect. And then the second one, so the course has a mini project as I mentioned last time. So we're gonna post some tentative project topics. They're not really like the exact subject that you have to work on. It's just like a high-level topic, high-level area that you can get ideas from. We point to some papers. These are potential topics. By no means I insist that you work on exactly those areas. Actually, ideally, I would like you to find a problem that is at the intersection of what you do in your own research and what you are covering in this course, basically online algorithms and online learning. But if you wanted to work on any of those topics, you should feel free. One thing I expect is that by the end of week 4, basically 2 weeks from now, you finalize the topic of your real project. And remember that you need to basically wrap up the project by week 9, because during week 9, in the class on week 9, you're going to do the final presentation and your paper or AKA report should be ready by that.
What kind of expectation you have?
We will see. No, I actually expect you to do something interesting. That has a broad meaning that, well, ideally you want to work on something new and maybe even have some partial results that you present to us during week 9, and then after the class you can continue working on that. That's the ideal thing I have in mind. But you know, you might want to do a survey of a bunch of papers, and I would say that might even be harder in some sense, because what I expect if you try to write a survey, then you need to understand a couple of papers that are connected to each other and present them in a connected fashion. Not that you present 5 papers, each one separately. You really need to kind of find a coherent way of presenting all of them under the same framework. Somehow similar to what I do, actually what we do as we are designing our materials. So if you want to do that, feel free, but my recommendation is try to actually work on a research question, maybe a small research question, that ideally you can continue working on it after the class. All right. Any partial progress is fine. And I like to see that partial progress both written in your paper and also presented in the class on week 9. Okay. Yes, ma'am.
And what do you mean by research question? Because you are providing us with a general area, yeah?
Yeah, you should dig deep and find a question, an open problem. I mean, I would be happy to actually give you more concrete recommendations. And I probably add 1 or 2 questions, like general questions, not really at the level of, hey, here is this concrete problem, go and solve it. Just like at the level of, hey, this research question, research agenda, I think it might be relevant, go and do research and let us know what you find out. Yeah. That's the idea of mini project. Any questions? I have a question for you. How many of you are familiar with assortment planning? 1 person, 2, 3, right? So the main thing that you're actually going to cover today is assortment planning and how to do that in real time in a sequential decision-making environment. But before that, I will actually cover the basics of assortment planning, very, very basics. What does that problem mean? What are the applications? So the way to think about assortment planning is this is one of the core operations that an online retailer or even classic retailer like Zara should do. So the question is, in each season, as a manufacturer, you want to decide on a subset of products that you display to the consumers of your product. Like, for example, imagine that I'm making a bunch of decisions in each season as a manufacturer. In season 1, I'm going to pick a subset of available products, put that in my store, and then consumers come, there is a model for the demand, they make a choice, and we're going to formalize that in a second. So they make a choice, from the choice of the consumers some revenue will be generated, and then you go to the next season. Probably you have some inventory restrictions. Now the question is, how would you make these sequential decisions on which subset of product to display in each season so as to maximize your long run? This is more or less the type of question that people are studying assortment planning. So let's just start with the very basic question, which I call it offline assortment. And I'm gonna give you the semantics that in order to model this problem mathematically. Offline assortment planning or optimization. In this problem, imagine that you have n different products. I denote them by basically number 1 to n. And then each product I has a fixed, let's say, price equal to R. So this number, the price of different products, is not dependent on the demand. They are exogenous quantities that are given to the assortment block. This is one important aspect of this model. Then we have, let's actually be bigger, so we have these n different products, 1, 2 to n. So the assortment planner displays a set. And before that, let me actually define something else, which is an important part of the model. So I'm going to define this set, curly F, to be basically a subset of all possible subsets, a collection of all possible subsets of these products. And this is basically denoting the set of feasible subsets we can display or feasible assortments. All right. Now, the platform picks a subset S of these products such that this set is actually feasible. So S should belong to this curly F. And displays this set, this subset of products, this subset to a consumer. Right? So we have, let's say, these products. You pick a subset, S, which is feasible, belongs to this collection. And for simplicity, just by default, assume that the collection contains all the possible subsets. We are going to later talk about other feasibility environments, but for now, imagine that any possible subset is feasible. Right? So you output this set. Now a consumer comes, looks at this set, and makes a stochastic or randomized choice. So the consumer picks something. I'm going to denote it by, let's say, I of S. So I of S is one of the elements in this set. And it is actually a random variable. So we can say that the probability that I of S is equal to some certain I is equal to a function phi that has two input arguments. The first one is the subset, the assortment. Actually, let me make this the second argument. The first argument is the I, the element, and the second one is S. So this is going to be the assortment. This is going to be product. Okay. So we model the consumer choice using these property distributions for each set S. We know the summation of phi I and S, or all I in S, is at most 1. And this is not exactly 1 because we always assume, this is very important in assortment optimization, we always assume that there is this dummy item, I call it outside option. And if the sum of these properties is not equal to 1, then the consumer essentially goes for the outside option. In other words, for each I in S, phi is the probability that element I is picked. And then 1 minus summation of phi s will be the probability that the consumer goes with the outside option. So there is always a chance that the consumer doesn't pick any product. Any questions about the basic model? Yes.
So the assortment is going to be different for all the different consumers, or?
So in this basic problem, the offline one, I assume just there is a one consumer.
Oh.
So you have one consumer, you know the consumer. So we call this thing consumer choice form. So the collection of these numbers, CIS for every possible I and S, I usually refer to it as the consumer choice model. So consumer is modeled by the consumer choice model. Here I assume that I have one consumer, the choice model is given, and a platform is trying to pick a subset. So what is the goal of the platform? The goal is pick a subset S star that is feasible such that S star is actually one of the sets that maximizes expected revenue you can get from a set S. And let's write down that. So the expected revenue would be the summation over I in S. Element I is going to be picked with probability phi IS. And if that element is picked, the revenue generated is going to be equal to R, the price of the product. So the goal of the assortment planner is pick a set S that maximizes expected revenue. Right. Now let's try to actually look at some examples. So the first example is a generic choice model called random utility model. So example 1. Random utility model for RUM. So what is this model? This is a way of describing the choice model. So how do you describe that? You have n products. The consumer has a utility for each of these products, but the utility is a random variable realized from a given distribution. And usually the assumption is that these utilities are actually independent. And let me make that assumption as well. So I have these n different products. The consumer comes. Remember that each product has a fixed price, R1, R2 to Rn. This is the price. And then from the perspective of the consumer, there is a utility. If she gets this product, I denote that by U, U1, U2, all the way to UF. And imagine that this UI is realized from some distribution, Fi. And just for simplicity, assume that UIs are independent. But definitely you can think of the random utility models where UIs are also correct. For now, just assume that they're. Now, what does the consumer do? So the consumer, so if you show the consumer a set, let's say I show a subset S, so then the consumer picks I of S, again a random variable, which is the one item that has a maximum utility. So argmax UI for all I in S. Right. So then you can say from this description, phi of I and S, the probability that given set S, the consumer picks item I, is essentially the probability of an event where, let's say, UI is greater or equal than all the UJs for J in S minus I. And imagine that these are continuous distributions, so essentially no tie happens. It's a zero measure event. Then if UI, the utility of the item is greater or equal than UJ, then, and oh, actually this is also important. So to incorporate outside option, I forgot to say, so I'm gonna always add this outside option. And let's say we set the utility of this guy to be 0. So u of 0 is equal to 0. It can be just like some deterministic number. But the purchase happens. So I guess it's gonna be this thing if essentially u of is greater or equal than 0. Otherwise, is will be the outside option. This is the rule. And then the probability is the probability that ui is greater or equal than uj for every j, and ui is less than greater or equal than u0, which I assume to be 0. And for this model to make sense, basically, you give a possibility to the consumer to pick an outside option. You have to think about a distribution that gets negative numbers, or if you have a different distribution, then maybe you want to change u0 to some other constant. So the model has a lot of bells and whistles, but it is actually fairly simple. Now let me give you an example of the random utility model that you have seen. I believe Warren, it was the final exam of the previous course, right? Multinomial choice. Multinomial choice model. And this thing is called multinomial logic choice model. Essentially, it goes by the name by abbreviation of MNL. Actually, let me do the multinomial logic to make sure. Choice model, MNL. So what is this choice model? Is a special case of random utility model where you're picking a particular distribution for UI. So assume that, so it is random utility model when UI is realized from what they call the Gumbel distribution. And I'm going to explain what is this distribution. Gumbel, actually, let me sorry. So UI is equal to some WI, so this one is a fixed constant, plus epsilon I. So imagine this is just a constant dependent on I. This is not a random variable. And then epsilon I is a random variable that is realized from Gumbel distribution, a standard Gumbel with parameter, the scale parameter 1, and then the central parameter 0. So 1 and 0. So what is this distribution? CDF, f of x, which is the probability that epsilon is at most x, is equal to e to the power of minus e to the power of minus x. In fact, it has an interesting connection with exponential distribution. If epsilon is a standard Gumbel, and if I look at minus ln of epsilon, then this is going to be an exponential random variable with mean 1. And let's actually show this because this is a lemma. But I'm going to use that in order to write down a very nice form for the consumer choice model. This is fairly easy, right? So let's call this guy Z. So the probability that Z is smaller than X is equal to the probability that minus ln of epsilon is at most X. So this is equal to the probability that epsilon is greater or equal than e to the power minus X. made a mistake. So I think this is the inverse of that function. So this should be, let's see, yeah, sorry. So e to the power minus epsilon should be exponential 1. Let's do that. So it is now probably that e to the power minus epsilon is at most x. I should have written this down. And this is the probability that epsilon is greater or equal than minus ln of x. Excellent. So now if you plug this into here, this is 1 minus the CDF of Gumbel at the point minus ln of x, and this is essentially e to the power minus e to the power of minus ln of x, so e to the power minus x. And this is the CDF of the exponential distribution. So why did I highlight this lemma? Because now, and actually let me show you another, just like I mentioned a version of this lemma. So I believe if you look at ui, e to the power of minus ui, where ui is the Gumbel plus some constant, now is going to be an exponential random variable with mean equal to e to the power of, let's see, minus wi. Yeah. This is the mean, it's not the range. And just to prove this is like the same calculation, I'm not going to repeat it anymore. But now here is the funny part. So suppose I show you a set S, and I'm going to look at the probability that in a competition between these Gumbel random variables, I wins. So phi of I and S, or in the assortment problem, is going to be the probability that ui is greater or equal than, let's say, uj. Here, I'm going to use actually, right, so there is a u0, which is just epsilon 0, so w for the u0, the outside of change is going to be 0. So I'm going to have basically one ui for each of the actual items and one noise for the outside option. So this is going to be the outside option. Okay, good. So I is going to be selected if ui is going to take on all the uj for j in s minus I union 0. Okay. And now you can just say this is equal to the probability of the events that e to the power minus ui is actually at most e to the power minus uj. Basically, this e to the power minus ui is the smallest one among all the e to the power minus u's. For j in s minus I union 0. And we know these guys are exponential random variables because of the lemma. So each of them, so this is the exponential random variable with the rate e to the power wi, and this is the exponential with rate e to the power wj. So what do we know about the exponential rates? So I have a bunch of independent exponential random variables with different rates. And I'm asking, so they start the rate, so basically you realize this exponential random variable. What's the probability that I is the smallest one? It's a famous property of exponential random variable.
It's the average, it's the parameter over the parameter of the other.
Excellent. So it's basically so the probability that I wins an exponential is proportional to the rate of the Poisson process, which corresponds to that exponential, or it is proportional to the 1 over mean of the exponential. So this is now going to be equal to e to the power wi divided by, remember, so there was one exponential random variable with w0, which gives you a e to the power 0, that's the one. And then there were some others, e to the power wj, j in s. And that would be the probability that
Should
I
be
is.
minus,
What's that?
it should be minus wi.
No, so the rate is,
Yeah, the mean appears here and the rate
so
is
the rate
being
appears
was-
here. And the rate is actually e to the power wi. The mean is e to the minus wi. So the one that has higher rates, a smaller mean, is more likely to win the race.
But the point is, when wi goes to infinity, it should be equal to 0, right?
No, so if wi is infinity, so this is a very attractive option. So you're gonna pick that equal to 1. Right?
Oh,
So-
okay, I see. Yeah.
So basically, if you have an item whose wi is way larger than the other items, you're always picking that item. And it always also wins the outside option. Yes.
That's the softmax. That's the softmax, right?
It's almost a softmax, yeah.
I mean, if you have w0 equals 0.
Yeah. I love this connection to softmax. Let me actually say it because Constantine have. So another way to get this distribution is trying to, let me break it down. So I try to, let's say, the it's a regularized version of maximum linear program using negative entropy. Let me actually break it down. If from this class the only thing that you learn is this thing, I think I'm happy enough. Connection to softmax. So imagine it's a thought experiment. So suppose I give you n different options. And options. The value that you have for option I is e to the power wi. So e to the power w1, e to the power w2, all the way to e to the power wn. Sorry, actually w1 to wn. So the values that you have are w1 to wn. Okay. So I have two agents. So the first one is max agent. The other one is a softmax agent. So what does the max do? The max basically solves the following simple linear program. So it tries to, so the goal is, these guys are going to select one of these options. And let me use x1, the vector x, x1 through xn to denote the selection. So for example, if I pick one, x1 is 1, the other x's are 0. You can also have randomized selection, which is going to be any distribution over these n items, okay? So the max is going to solve a very trivial linear program. It's trying to maximize summation xiwi subject to summation xi to be at most 1 and xi to be greater or equal than. And the solution is trivial. You just put all of your mass on the I with the maximum W. Now, what does the softmax do? So softmax, or the logic regression maximum function. So it's basically maximizing the same linear objective. But this time, it's going to regularize this so that you have more tendency to pick a uniform distribution. So what's the distribution? So what's the function for which the uniform distribution is maximized? Entropy. I don't know if you're familiar with entropy. So it's basically, I have a distribution over n options. I look at the entropy of this distribution. So the entropy is defined to be minus summation xi ln of xi for all i's. So if I'm just maximizing entropy, I'm going to pick the uniform distribution. If I'm just maximizing the linear term, I'm going to pick the max. This is a regularized version of maximum. So you're trying to maximize this subject to x being in the simplex, basically the summation of x equals 1. And if you solve this thing, the answer is going to be exactly that. So xi star from this optimization is a concave optimization problem. So xi star is going to be equal to essentially e to the power of wi divided by, in this case, summation of e to the power w j's over all these n options. And if I restrict my max to pick its option in a set S, given the outside option that has W0, then this is going to be exactly that distribution. Right. Okay, so too much about assortment. I want to highlight the property of all these choice models because it's essential in the rest of the lecture. So let me collect the property. And the name of the property is essentially Vic substitution. So what does Vic substitution mean? So imagine that I give you an assortment. And then I look at one item in this assortment. So with some probability, you're going to pick that item. And this is determined by the choice model. Now suppose I give you less number of options. Do you expect to pick this item with a higher probability or lower probability? Higher probability. So this is, I mean, when you say expect, let me give you an example that doesn't make sense. So suppose I'm selling left shoes and right shoes. And then you can also buy two items. And I give you like a bunch of pairs, some left and right, some left and right, and then there is this left. So if you look at the probability that you buy the left one, then the probability is 0 because you want to have a pair of shoes, so you never actually buy the left one. But if I give you the right one, then the probability that you buy left is going to increase because left and right are complements to each other. But then in some applications, the products can be substituting each other. So basically, one product is going to cannibalize the choice of another product. For example, you need some number of you need milk, and then there are different brands that provide milk. So if brand 1 is available, then you're going to go with brand 1. If brand 1 is not available, then you're going to go with brand 2. So in these cases, if I give you more options, the probability that you pick each of them is just going to be a small. And in fact, the random utility model has that property. Why? Because, well, so you have certain utilities, random, just pick even like a realization of these random variables. I give you a set, you pick the I that has maximum UI. Now, if I kick out some of the elements, then the probability that I is maximum only goes up because the competition is less in some sense between these items. And this property is called Vic substitution. Mathematically speaking, we say a choice model is Vic substitute if for every two sets, let's say S subset of S prime, and any item I in S, I can say the phi of I and S is at least the phi of I and S prime. Very simple. Okay. So in this lecture, we are only focusing on Vic substitute assortment, and actually life is usually much easier in the world of assortment optimization when you think about this type of consumers versus consumers that have complement, or when you have products that have complement. Any questions about the assortment? Because then I'm going to switch to the online assortment problem. Okay, great. So from now on, every time I said the offline assortment, I really mean this optimization problem. You're going to pick a set that maximizes the expected revenue given a choice one. Okay. So what is the online assortment problem?
Yes.
Yes.
How do you solve that?
Great question. Exercise. So in general, this is, so let me give you first an answer and then I'm directing you. So this is the optimization over 2 to the n options. So it seems to be non-tractable at the beginning because you have to maybe try all different assortments. So this is the entire literature on how to do assortment optimization either exactly or up to approximations in polynomial time. And so definitely for a general consumer choice model, it's not possible. But then there are certain consumer choice models that make sense in practice. And then for them, the assortment optimization problem can be done either exactly or approximately in polynomial time. And one example is actually MNL. And this is my exercise. And this is really a good exercise, especially if you're doing OR/OM. I think this is one thing that you should know by heart. If you're doing OR/OM and you're also interested in revenue management. So what is that thing? So if choice is MNL, then optimal assortment SS star is going to be one of the revenue order sets. What does that mean? Suppose without loss of jointity, I sort the items so that R1, the price of product 1 is greater than R2, is greater than Rn. Okay. Then here is the exercise. So it says that SS star is gonna be the one assortment which is a prefix of this sequence, but it can be any of them. So I look at basically the n sets, basically starting from item 1 all the way to item j. I look at the revenue I can get from these things, where the R of S is defined to be basically the summation I in S, yeah, I n S times R. So it's the expected revenue you can get from a certain subset. So all it says that, rather than looking at all the 2 to the n subsets, you can just restrict your attention to n a specific subset, the revenue ordered one. How you would define them? Index your items in a sorted fashion. So R1 has higher revenue than R2 and has higher revenue than Rn. You only need to look at these prefixes of different lengths. And one of them is the one that maximizes expected revenue.
So that's linear, yeah, the cost.
So in linear time, we can actually solve this problem. Exactly. This is very nice. And there are versions of this that generalize. So there's a generalization of the multinomial logits called Markov chain choice model, and then for Markov chain choice model, something similar to this holds. But this is the extent to which these kind of like nice structures appear. There are variations of MNL that are extremely hard. For example, if I give you a distribution over different MNLs called mixed MNL, then that problem is actually pretty hard. It's APX hard, so there is no polynomial time algorithm that can give any constant approximation for a last optimization problem. But if the support of the mixed MNL is just 1, then it is a very easy problem. So it's kind of like a very structured results. If you play with the structure, this is not going to be true anymore. Yes, Hans.
Also, why our utility function doesn't relate to
The price.
Yeah.
Yeah. So this is one thing that is really missing in this model. That your choice has nothing to do with the price. I think this is not really a good assumption. But in the application of retail, somehow these utilities are capturing your behavior, and maybe implicitly they're capturing the price of the product as well. So somehow WI here can be a function of price, for example. But everything is exogenous. There is no endogenous behavior here. And there are other econ models. So this is more of an OR model. So econ models that capture choice. And some of them capture this fact that your demand is elastic to price. But this one doesn't, in some sense. I mean, you can definitely let WI to be a function of price and somehow in a very superficial fashion, you're capturing the demand to price elasticity, but that's the extent to which that you can incorporate that behavior into this model. Yes, sir.
So why is this a specific choice of noise? Like, does this hold like to be a good model in practice?
There are a lot of empirical evidences that this model is actually fairly bad. I would say the most important reason that people like this is because it captures the big substitution in a way that the problem is tractable. And there are certain applications in which this very simplified assumption is true, but definitely if you ask a retailer, like let's say I ask Zara whether you guys are using MNL, they're just going to laugh at you. No, actually we use the data in order to predict the consumer's behavior. Maybe they train a deep neural network at this very simplified choice model.
So it's like easy to estimate as a marketing guy, right? Based on sales data, you can estimate WI easily. So there's like a probit model where it's normal. It's very hard to estimate numerically that model, for example. So for marketing people, they care about estimation.
Exactly. So parameter estimations of behavior is kind of like this very old-fashioned practice across industry. And this model is parametric with just n parameters. Now, I don't need to give you all these numbers. You just have n parameters to learn in order to specify the models. So in some sense, it is easier to learn. But contingent on this is actual behavior, and that's what is, I think, question. All right, so let me switch to online assortment. And we are gonna practice our Primal-dual skills again in this context. So in this class, I'm gonna actually talk about online assortment optimization from two perspectives. The first perspective is when you are pessimistic about the arrival of the consumers, and you want to have no assumption on that. So basically, we put our adversarial hat on and we assume that the input is adversarial. And then at the end of the class, I'm going to switch to the Bayesian model where the decision maker is endowed with distributional knowledge about the arrival. And the question is, how would you use that distributional knowledge in order to have better assortment planning decisions? Okay. So, but now we are going to talk about adversarial online assortment optimization. So what is this problem? So again, we have n products with prices that are fixed over time, R1 to Rn. There is a selling horizon of length t. So t is going to be the length of the selling horizon. We are discretizing time, so time is going to be one of the numbers 1 to capital T. Each product has a limited inventory, which is what's coupling different times together. So each product I has initial inventory CI. Let's say it's an integer. In the first part, we are more or less thinking about the regime where the initial inventories are large. And now, what's the game? So at each time t, here's a sequence of things that happen. The consumer with the choice model phi of t arrives. The platform displays a feasible assortment but only among the available products. So you have limited inventory, so you might actually run out of some products, so you're not allowed to assort an unavailable product. And then finally, the consumer chooses, let me denote this assortment by S of t. So then consumer chooses I of t and S of t from S of t, such that basically the probability that this I of t of S of t is equal to some certain I in set st is equal to the phi t of I and S of t. So it follows that choice model. And the important part is, you get different choice models because consumers might be heterogeneous, so you get different choice model over time, and you need to respect these inventories across time. Now the goal is to maximize the total revenue. So the goal is to maximize the total revenue in the entire selling price. Entire selling price. And by revenue, I really mean expected revenue. Is the problem clear? Yes.
You said the consumers may be heterogeneous.
Yeah, so these phi t's can be different over time.
I mean, if it's not, it won't be an online, it will be a dynamic program, right?
So actually, even if I give you the sequence of phi t's for time, let's say they are the same or different. It really doesn't matter. Even if you know the sequence of phi t's and you'll find a sequence of assortments that maximum expected revenue, this is still a dynamic program with exponential sizes because of the randomness in the choice.
But adversary can't do anything in that case.
So the problem has two challenges. So the first one is because of the adversarial arrival of these things that you don't know as the online algorithm. But even if you know that, being as good as the optimum policy now has computational challenges because you need to solve the dynamic program. And this is great because I was gonna introduce the Clairvoyant optimum offline, which is the benchmark we are gonna use here. This is exactly the one that Arvid and I talked about. So what is the benchmark? This is an online problem. Usually we think about, optimum offline price, right? So for example, last time we were talking about the adverse problem. If I give you the sequence of arrivals, then you could write a linear program that was maximizing the expected total collected, actually not expected, total collected bid, and that was the optimal offline solution. So here, because of this post-allocation and stochasticity, you can't easily write down an offline benchmark. But then you can start thinking, so imagine that I know the adversarial part of it. As an algorithm, you know the entire sequence of choices. So assume an algorithm knows phi1 all the way to phi capital T. Okay? So you know the choice model, but you don't know the exact realization of choice. Now think about it. So the state of the problem is captured by how many number of each units you have on hand at each time. Then you assort something, you go to a different state. Now you assort something, you go to a different state. So there is a Markov decision process with exponential size state space. Why? Because each state is captured by a vector of impossible inventory. So this is exponentially big. But like any other MVP, by using a dynamic program, you can solve this problem. So I don't expect you to actually know how to solve the MVP dynamic program, and I'm not going to actually use that. But just for a few years, there is an algorithm that will give you basically the optimum online policy, knowing when you know the consumer choices that maximizes expected revenue. But this policy is actually computationally, seems to be computationally hard. We actually don't know whether it is computationally hard or not, but we suspect that it is PS-based hard for this problem.
But we don't know.
Actually, there is no formal computational hardware for this problem. So there is a partially observable Markov decision process in general. So there is classic results by Papadimitriou and Tistikidis, which says that that problem is p-space hard. But it's a way more general problem than this. Even for the matching version of this, I don't know whether it is p-space hard or not. There's a recent paper by Amin and Christoph Papadimitriou that they look at the generalization of the matching problem, which is not actually a special case of assortment, and that one is again p-space hard. But this specific one, I don't know. Maybe even if you know the phi one to phi, maybe you will be able to find the optimal policy even in polynomial time. But it seems to be very hard.
Why is it POMD MDP and not just an MDP? It seems like,
It's not an arbitrary MDP.
but it's not a special case of a POMDP. I mean,
It's not.
yeah.
It's not.
I mean, the states are completely observable here.
I agree. So this is actually, it seems to be easier than partial MDP. But still at the same time, I don't know how to solve it in polynomial time. And if I want to give a conjecture, I would say this is going to be p-space hard, but we just don't know how to do it. But the most important part is that we are not talking about the online problem. We are talking about the offline problem, that if you get to see the sequence of consumer choices, and still the problem might be computationally hard. Right? Now, we don't want to know this. We are an online algorithm. We are in the online optimization class. So we want to design an algorithm that without even knowing this sequence can be a constant approximation to the Clairvoyant benchmark. So let me write down the benchmark. So Clairvoyant optimum offline. Basically, with the above knowledge, solve an exponential selective P. That maximizes total expected revenue. Sorry, I'm writing everything in words because these are really not that much importance. You just need to know what is this policy. And I'm going to call the revenue you get from this thing to be opt. Okay. So before going any further, because we want to design policies, the last time we saw that linear programming and Primal-dual is helping us not only to design a policy, but also to analyze them. Let's try to find out the linear programming relaxation for this problem, and then we are going to use that in order to design our policy and also analyze it. So imagine the following. So suppose you know the sequence. At the same time, I tell you, hey, you don't need to satisfy the inventory constraints. The only thing that you need to satisfy is the inventory constraints in expectation. So you don't have to exactly use at most CI unit of product I. So as long as you give me some choices so that the expected number of units of I that you produce or you sell is at most CI, you are good to go. Now we can start searching over S1, S2, all the way to ST. And then when you fix the sequence, you can give me two numbers. You can give me n numbers, the expected number of items that you sell given the sequence of cells, sequence of subsets. And then you can try to maximize an objective, which is the expected revenue you can get from this. So in particular, I claim that if you relax the feasibility constraints to hold in expectation, then you can write down a linear program that maximizes the expected revenue in this relaxed state. This is similar to what we call the example relaxation or expected LP in the previous course for the profit inequality problem. Let me try to write it on this board in this language. Expected LP. I'm going to write down the LP and then we'll give you an exercise to show me this upper bound. So here is the LP that we have in mind. So we are trying to maximize. What are we trying to maximize? So I want to look at the space of randomized policies at each time my decision variables are going to distribution over all possible or all feasible sums. Okay. Now I'm trying to maximize summation over T in T, summation over all the subsets. Just imagine that the feasibility set is a collection of all the subsets, just to make life easier. Summation over all items in S. Now I'm picking the subset S with probability X of T and S. Item I is going to be selected with probability phi T, I and S. And if I select a subset and the consumer selects the item, my revenue is going to be R1. So apparently from these distributions, each one for a subset of assortments at each time, this is the expected revenue you can get. So what are the constraints? So I expect each of these things to be a distribution. So for every T, you need the summation of X, T, and S over all subsets to the at most one. And XTS are non-negative. I'm writing it down here. And you have the option of not displaying it. This is why this is at most one. What is the other constraint? So we want to satisfy the inventory constraints in expectation, meaning that the expected number of items that I sell for each product should be at most CI. How to write that? So for every product I, this is the expected number of items that I sell, so the summation over all the subsets that include I. Actually, do the time first. So summation over all times. Summation over all subsets that include I.
And TAIS.
Right. So I pick item I if the set S is selected, which happens with probability XTS, and if the selection happens, which happens with probability VTIS, and this is now going to be the expected indicator random variable for this particular selection, and we want the sum of these expectations to be at most CI. Does it make sense? Okay, so another exercise, which is kind of very easy. I'm not going to show this because it's almost trivial exercise. Lemma. If I call this to be opt LP, then lemma says that opt LP is no less than opt. Basically, it's a relaxation for the Clairvoyant optimal offline batch. And just to give you a hint how to prove such a lemma, you should really think about the one sample path of the Clairvoyant optimum offline. Use indicator random variables for its operation. And then you will see that if you replace these X's and P's with their corresponding indicator random variables, then this is going to be the realization of the revenue. This is going to be 1 or at most 1. And then this left-hand side will be the number of items that you are selling from product I. But everything is a random variable. Now take expectation from both the objective and the constraints, and therefore the corresponding probability associated with the Clairvoyant optimal offline should satisfy this LP. And that essentially means that optimal LP is at most opt. Yes, Chen.
So how easy it is to solve this problem?
Great. As easy as solving the offline assortments optimization. And it might not be trivial to see why. This problem has exponentially many variables and polynomially many constraints. So every time that you see a linear program with exponentially many variables and polynomially many constraints, the way to think about it is looking at this dual, which has polynomial variables and exponentially many constraints, and then trying to see that if we can find the polynomial time separation oracle for the two. You will see in the next part of the lecture, we will see another linear program of this form. That if you look at the dual of this program, then the offline assortment solver is actually playing the role of the separation oracle for the two. And therefore, you can run the ellipsoid methods and do it with the separation oracle, or maybe another cutting plane method like YDS algorithm with the separation oracle. Then you find a subset of binding constraints through the running of the ellipsoid, because the ellipsoid is polynomial time, you will have polynomially many constraints of that form. These are the only variables in the primal that can have non-zero value. Now you go back to primal, solve it again, but restricting to that polynomial subset of variables, that gives you the optimal solution. Yes, this is essentially what we do. But yeah, so the dual can be solved in polynomial time, therefore the primal. Any questions? Yes, ma'am.
Here, what would be our feasible state? Because
Great. So you have like a feasibility condition. Let's say I'm not allowed to assort subsets of size at most 4, for example. And then these summations are going to be over that feasibility set. This is going to be over that feasibility set. It has nothing to do with the availability or not. Yes.
I didn't mean that. Yeah, I wanted to say, shouldn't we relate that to the availability?
Good. So when I say feasibility, what I mean is like something that is independent from availability or unavailability. It's like a restriction on the sets. But the ones that are relevant for assortment are downward closed sets, meaning that if a set S is available, then any subset of that is going to be available. For example, let's say my condition is saying that subset of sets should not be at most K. Then if a set has size no more than K, any subset of that has size no more than K, so your feasibility environment is going to be downward. Now, I give you a signal for each product, whether it is available or not, that comes from the past. If actual subset that you can display is a subset of available product, that is also the intersection of the feasibility environment with the availability vector, and this is always going to be a feasible assortment because of the downward flow. Does it make sense now? So imagine that here, in this line, you have to display a feasible assortment ST among the available products. So not all the products are available because you might run out of inventory for some other products. In the set of available products, now restrict the feasibility environment to this subset that gives you the actual set of feasible assortments that you can display at each time, at this certain time. And this is the set that you have to opt from. And my algorithm that I'm going to show you is very risky.
But we don't have that in our.
It's not that hard to incorporate it. Imagine I just like say, these. And this is all the S's in F such that I is in S. If you make these 3 changes, then you will only consider distributions over physical substance. Here, you don't have to assort an available subset of products. That's the important part. Because you don't want to satisfy feasibility constraints point-wise. You only need to satisfy the feasibility constraint expectation.
Yeah, but we kind of haven't relaxed that uniformly over some kind of uniform notion because
it doesn't need to be uniform because these fees are different across time. And this LP is actually capturing how should you distribute your revenue across time. Like, for example, if I Lagrangeify this constraint, the problem even decouples across time, right? And then you really know how much revenue you get in each time. It doesn't need to be uniform because maybe in some certain time, the consumer choice is something that you can't extract that much revenue from that time. But it's going to be something that is captured by this. So now, let me, because we saw the technique of how to use the dual of the linear programs in order to design online algorithms last time. Let me directly start with the optimum online algorithm there in the large inventory regime, which is very similar to the adversarial algorithm that we saw last time for search ads, MSPD algorithm. But before that, let me ask you a question. Actually, let me write down the dual of the LP so that I answer Chen's question as well. So we are going to have two sets of dual variables. Let's use lambda t for these constraints and theta I for these constraints. What will be the dual of the LP? So the dual LP, you're trying to minimize over lambdas and thetas. What is the objective? It's going to be the summation of lambda t's, t in t, plus summation of ci theta i's, I in n. What are the constraints? For each primal variable, you are going to have a constraint, which means for every time and for every subset S, I'm going to have a constraint. So what does that constraint say? Basically, you need lambda t plus, now let's think about this. I multiply theta I by things, and I look at every single term in which XTS appears. So every time that I is in S, XTS appears in that summation. So that means that my dual is going to be, the other term is going to be lambda t plus summation, all the i's in S, and then you get theta I times phi t of I and S. And now this should cover the coefficient of the primal variable XTS, which is ET, which is sum over all the I in S, phi t of I and S times R. Sorry. And everything should be done. So similar to last time, in order to design an online algorithm, we are going to start with the question that if I give you an extra information, which is the optimal assignment of the dual variables, in particular theta I star, what would be an online algorithm that seems to be the optimal one? Or in other words, if you think about this board in which you don't need to actually satisfy the dual constraints 0.5 and you want to satisfy the inventory constraint 0.5, you want to satisfy the inventory constraints only in expectation. But the still is an online problem, meaning that you get to see the choices one by one. If I give you the optimal assignment of the thetas, what would be the online algorithm that maximizes expected revenue subject to all the inventory constraints to be satisfied in expectation? Right. And I claim that if you know this extra information, theta I star, similar to last time, you can actually have an algorithm that is as good as the expected outcome. Let's think about these. Similar to last time, we're going to look at the complementary slackness, for these constraints. So what does it say? So it says that, hey, so the constraint itself says that lambda t should be greater or equal than summation I in S Ri minus theta I times phi t of I and S. And then looking at complementary slackness, we know that either XTS, the private variable corresponding to this constraint, is 0, or it is greater than 0, and this constraint is tight. So lambda t should be exactly equal to the summation I in, so say, let me actually use a different notation. So either XTS hat is 0 or XTS hat is greater than 0, and lambda t is equal to the summation I in S hat, Ri minus theta I, phi t I and S hat. So what does it say about S hat? So if you have a tight constraint,
Should it be XTS or summation over SXTS?
sorry, what? I'm looking at.
Should it be summation over SXTS?
No, it's like the primal variable corresponding to this constant, which is XTS. You have one variable for each t and each s.
Oh, right.
Yeah, so imagine that at some certain subset S hat, XTS hat is greater than 0. And this is tight. And you know that for any other set, this is greater or equal than, so lambda is greater or equal than this right hand. So what does it say about this particular set S hat? Optimum solution of an offline assortment problem where your revenues are, or your prices are this one. If you look at RIT, let's say let's call it virtual price, and the virtual price is equal to Ri minus theta I star. This is, by the way, the optimum assignment of the dual. Then if you solve the offline assortment problem using these guys, and find the set S hat, then this is going to be the one that in the optimal offline solution you're allowed to use in the support of your distribution. And in fact, similar to last time, we can design the magician-based algorithm, which is the online algorithm is endowed with the dual. At each time, you solve just an offline assortment problem by changing the prices, decreasing the prices from Ri to Ri minus theta I star, and you just ignore the future, solve this offline assortment one by one, and then the sequence that you end up with, because these thetas are optimal, will be actually giving you the solution to the t. This is coming simply from the theory level. Exactly similar to last time.
But this is partially Lagrangeifying it.
Yeah, so basically if you partially, so if you partially Lagrangeify this constraint, the primal constraint, the capacity constraint, bring it to the objective, then if you set the Lagrangians with the optimal Lagrangians, each price will be decreased by the theta I, and the problem decouples across time. And for each time, you have to really solve an offline assortment where your prices are going down by theta I star. Right? But we don't know theta I, and we're going to design an online algorithm. What did we do last time? So we looked at the current consumption level of the product. If you remember, for the display ad or search ad problem, so we looked at the current consumption level, and we said, okay, so we are gonna set theta i's to be a nonlinear mapping of the normalized consumption level of each product. And then we use those theta i's here. And it turned out to be the optimum, or let's say the best asymptotic online algorithm when capacity is very large, right? So let's do exactly the same thing here. I'm not writing the details that I said because they are exactly equal to last time, but let's introduce this algorithm. So the algorithm is called inventory balancing. And this is just an extension or generalization of the algorithm that we saw last time for the adverse problem. So inventory balancing or IB. Here's what it does. So the algorithm uses the function G. So let me write it here. It uses function G, which is a mapping from 0, 1 to 0, 1. If you paid attention to the last lecture, we were very obsessed with a particular mapping G of X, which was e to the power X minus 1 divided by e minus 1. But for now, just imagine it's an arbitrary function. As you will see, I'm going to use this particular mapping. Let's also define the consumption level. So YIT would be the number of units of product I that are sold by the beginning of time t. By the start of time t, YIT is basically that you look at different products, YIT is how many number of these products you have sold. So YIT starts at 0 and it can never go above CI during this process. Right, so this is the number between 0 and CI for each. Right? So here is, and just to keep in mind, G of 1 is equal to 1. Okay. And why they say that? Because I'm going to use that. So the main idea of inventory balancing, so let me write it here. So the high level idea is somehow keeping GI, theta i's, to be equal to Ri times G of YIT divided by CI. So this is the high level idea. So you try to imagine in your head that the dual is equal to this quantity. And then assuming that this is the optimal, even though this is not the optimal dual, assuming this is the optimal dual, follow the recipe that you have when you have access to the optimum duals. And then they show this is going to be a 1 minus 1 over E competitive online algorithm in the regime where the inventories are reached. So what is the exact algorithm? So it's just simple. At each time t, you give one query to the offline assortment solver. At each time t, pick a set st such that it maximizes summation over all I in S, Ri times 1 minus G of YIT divided by CI. So I'm basically giving a discount to each product, a factor of 1 minus G of the normalized consumption of the product, multiplied by the choice function. So that's it. All right, so let me prove a very simple claim about this algorithm, and then we're going to have maybe 7 minutes of break. Yes, Mohammed.
And what's the intuition behind multiplying Ri to our applied G on the normalized value?
Oh, you mean why do I have Ri here, but I didn't have? That's a great question. Basically, it's about kind of like normalization. This is something that we didn't have last time, because somehow the normalization factor here and there, they're very equal to each other. So this theta should be actually, so the optimum theta will be proportional to Ri. So in some sense, if I multiply all the Ri's, let's say by 2, and I solve the dual problem, then all the thetas are going to be multiplied by 2. So you need the theta to actually scale with Ri. Last time you didn't need because of the fact that if I multiply the budgets by some number, the problem becomes a different problem. So you need to multiply the budgets by some number and bits by some same number, and then the problem will be this. This time, if I just like multiply the RIs by some number, then more or less you have the same problem. Right? And that should be captured by theta.
Also, the units don't match if you don't multiply.
Right. Did I answer your question? That's the intuition. So here's a funny fact about this algorithm, and then we're going to have to bridge. Let me not erase my dual. Just write this funny fact here. Yeah, I hate when this happens. Let me find it. So, the funny facts claim inventory balancing always return a subset of available products. Remember, saying this optimization problem, I didn't say look at the subset of available products, just said among all the feasible subsets. Forget about the availability or unavailability. Pick the one that maximizes quantity. And I claim that inventory balancing always return a subset of available products. If you do the tie breaking correctly. And why is that?
G of 1 is 1, so ST, I mean, this thing becomes 0 for all the sets for which.
Exactly. You see what's happening? So if G of 1 is 1, and claim
This is under weak substitution, right?
what's that?
This is under weak substitution.
Under weak substitution, right? So if G of 1 is equal to 1, under weak substitution, so you have the option of assorting the larger set that has some items with revenue 0. But then if you shrink it to the smaller one, your revenue weakly increases. And this is why I say you need to do tie breaking, because we don't have a strict weak substitution. We don't have a strong substitution, a weak substitution. And because of that, you might actually end up having two options. One option has a bunch of items that are unavailable and have 0 virtual price. If you happen to have those items, just do not assort, do not put them in your assort. My claim is there is always an argmax here that only contains available products. Because for any unavailable product, this normalized inventory is equal to 1. We assume G of 1 is equal to 1, therefore 1 minus G of 1 is 0. The virtual price for that product is going to be 0. And then now, okay, so imagine you find this argmax, it has a subset that is available and a subset that is unavailable. The unavailable ones are not contributing to your revenue. If you get rid of them, then for the remaining subsets, the probability of selection for every single element there is just weakly going up. That's the property of weak substitution. So you're weakly better off returning that subset that only has available products. Okay, let's take a break for 5 minutes and then I'm going to show you the proof of this theorem.
So the way we wrote this problem, we assume phi t is available to us at time t. But isn't that too strong in real world, like that an assumption? Like,
Yeah, so there are versions of the problem in which you have a consumer type, and the type is the encoding specialist model, and then there is a type distribution. So you either know the distribution or you don't know the distribution, and there's the IID. And in both cases, actually, you can learn.
I think it will not fit like this because size. So do you have backup in the drives?
1 minus 1.
Because when I look at that, just
Minus 4.
when I try to remember.
Do you know why?
Like
What are the
I think you erase the complementary slide. No. It's like my problem. If you choose the maximizer, how do you know it's
It should be one.
yeah, because you Lagrangified that, and then we needed one constraint that, like before you told me, I think that beta was always less than one at the previous
Switch
problem.
your
So something like beta was less than one, and then that Lagrangified is that coefficient is positive, so we
Right, so here that means that theta I should be at most Ri. In fact, in the optimum solution, if theta is larger than Ri, we can always bring it up. So imagine that you have some theta that is strictly larger than Ri. I claim that it cannot be the optimum solution.
yeah, you
Because I just cap it to Ri, objective goes down, this constraint remains to be satisfied.
I don't know if you already sent me the feedback. That's what we want. I'm not sure. Okay, so
I wrote down the theorem I want to prove on that whiteboard. And we are going, so this is the theorem. So expected revenue of inventory balancing is going to be at least 1 minus 1 over E minus order epsilon times up till P. If you know that the minimum initial inventory of all the products is at least 1 over epsilon. Okay. Let's try to prove this. And I'm not gonna erase this one. Let me actually erase that pointer. So the proof is more or less similar to the proof that we saw last time. I'm going to do it quickly so that we have enough time to cover the Bayesian assortment. Basically, we need to construct a dual that certifies the approximate optimality of price. So proof. So we are going to construct an approximately optimal dual assignment. I'm denoting them by, let's say, lambda t hat and theta I hat. So we're gradually building this dual similar to before. So at the beginning, I'm going to have my, so initialize the thetas, initialize theta i's to be 0, lambda t hats to be 0. Okay. So now at each time t, suppose inventory balancing returns a set S of t. All right. So the choice of theta is easy. What we are going to do is the following. So the consumer chooses let's say IT from ST, where IT is realized from the distribution VT, I, and ST. Right? This is how we think about the stochastic choice. So we always want to keep an invariant where theta I hat is equal to G of the normalized inventory level or normalized consumption level of each product. And when the consumer chooses IT, the only product consumption that changes is the one for IT. So now what I'm going to do is I'm saying theta of IT hat will be equal to the previous theta IT hat plus Ri times the G of YIT at time t, which is the initial inventory plus 1 because it goes up by 1 divided by Ci minus G of YIT and T divided by Ci. And note that G of 0 is 0. I'm writing it somewhere here, which is important. Okay, so this is how you update data.
Is the reason you're right, not just telescoping everything and then
Yeah, let's do that, right? So basically what Varun is saying is, this is just a fancy way of writing down that, hey, at each time, I'm setting theta I for every single thing, right? For every single product, including the one that I picked, to be Ri times G of YIT final divided by Ci.
CAT.
CIT. So CIT is fixed. Ci is the initial inventory. Yes.
That is why IT final is.
Yeah, so this is basically the consumption at the beginning of time. So the way I defined YIT, let me write it again. So YIT was the number of sold units of I at the beginning of.
So isn't it equal to YIT plus 1?
Let me write it at the beginning of T. So for some of the items is equal to YIT, for those that are not picked. For just one item, the IT is equal to YIT plus 1.
No, YIT plus 1. Oh, okay.
Right.
Okay. That's
So there is one item, IT, that is picked. For that one, you get basically Y of IT and T plus 1 as the new consumption of the item, normally divided by Ci. But then for the remaining item, it is the same. So in the layman language, you're really trying to keep an invariant, which is theta to the R times G of normalized inventory.
But all of this
Normalized
should be IT.
consumption.
All of this should be IT because we're only updating it for IT. CI should also be CI, right?
CI should be something. Oh, this is what you meant. Oh, sorry, you're right. But you know, this is what I mean, essentially. For every single I, it should hold. Yes, Fab. Question.
What did you call IP? Is it the algorithm or is it the oracle?
So the algorithm returns a set, but then the consumer from that set is going to randomly pick one of the items from this distribution. So it's like, and the algorithm I display you a subset of products, then you're the consumer, you come, you choose one, you go to the next one.
so Oracle based on the current theta. The theta hat I have right now uses that as.
Okay.
isn't YINT final equal to YINT plus 1?
For only one product, the one
Why not
that,
all of them?
well, you're not picking,
One.
sure. No, I mean, if, so definitely what is the better definition of I? It's the number of sold units of I at the beginning of T. So if you don't sell any unit of I during that time, then the YIT final is going to be YIT.
And it's equal to YIT plus YINT plus 1. All three is equal.
YINT plus, oh, well, sure, I can use, oh, you're saying I could use T plus 1 here, not YIT.
Yeah, when you define
It's your final,
sure.
new terminology. Okay.
Okay, you're absolutely right. Let me write it down. So Muhammad Reza's version, and this should be
It's
written down in
recorded for
the script.
posterity now.
Yes. So this should be written down in the script. So Muhammad Reza's version Ri G Y I T plus 1 divided by C I, and I add this is the smarter version
It's for all right.
for all I. Right. Good. So this is the assignment of theta. What do we know about lambda? Just as a recap. So if I give you the optimum solution, then you know how to set lambda. So it's going to be basically the expected revenue that you could get from that set if the price of each product is Ri minus theta. And I'm going to do exactly the same thing. So lambda t is going to be set to be the summation I in S of t, this particular set. Ri times 1 minus g of yi divided by ci times phi t of I and st. Yeah. Okay. All right, so now let's try to show the things that we always show. First one is why the dual is feasible, and second is why the change in the primal is an approximation to change in the dual. So the first question, can everyone see this? So why dual? Oh, let me point out to something. This is actually important. This is a random variable this time. And this is kind of in contrast to all other dual assignments that we have seen in the previous lecture, because nothing was a stochastic in those models. So your dual weren't random variables, but this dual is really a random variable. This one is not, but this one is actually a random variable. And if you want to show its feasibility, what does that even mean? Now I'm gonna essentially say, okay, my final dual assignment.
So this is also a random variable. YIT is a
It is also random. You're absolutely right. So both, because YIT is a random variable. You're absolutely right. So therefore, let's actually do exactly what's the correct. So the final dual assignment that is going to show the approximation factor that you have in mind is really the expectation of these guys. So I'm going to look at the expectation of theta I hat, and let's call that theta I. And I'm going to look at the expectation of lambda t hat, and let's call that lambda t. So these are going to be the final dual assignments that I'm going to use. Okay. So now why the dual is feasible. Anyone has any questions about this trick? So in principle, you don't need to actually give me the duals in an online fashion. This is very important. So the primal algorithm is an online algorithm, but maybe at the end of the run of the algorithm, you can give me some dual assignment. And this is actually one of those cases because, well, so for every sample path, you can find this assignment, but you eventually need to run this for a lot of times in order to be able to take the expectation sometimes. So I'm not constructing these duals in an online fashion. Okay, I'm just taking samples from these duals in an online fashion. But eventually, what I have in mind as my dual assignment are the expectations of these random variables. And I'm going to show this is enough for certifying that primal is approximate. Okay, so why this dual is feasible? It's kind of easy. Right? Let's think about it. Expectation, basically in each sample path, I know that lambda t, so let's look at the left-hand side of the dual, so lambda t plus summation I in some set S, and then I look at theta lambda t hat, sorry, theta I hat phi t I and S, right? Okay. So what do I know about these two terms? I know that this is definitely greater or equal than lambda t is equal to this term. And remember, this is exactly what the inventory balancing is maxing. So therefore, if you replace ST with any other set, including S, then this quantity is going to only become a sum. Therefore, lambda t is really greater or equal than the summation I in S Ri times 1 minus G of yi t divided by Ci Ct of INS. What do I know about theta I hat? Theta I hat at the end of round t is actually equal to Ri times G of yit plus 1 divided by Ci. And this is just greater or equal than G of yit divided by Ci because G is a monotone increasing function. So therefore I can say this guy is definitely greater or equal than G of yit divided by Ci times Ri. And that gives me summation in S Ri G yit divided by Ci Pt INS. And now we see what's happening. So these are canceling each other. So this is greater or equal than summation I in S Ri Pt INS. And that shows that, well, so these guys actually are pointwise feasible. Now, if I look at the expectation, so if you take expectation from the left-hand side and right-hand side, still the same inequality holds, and therefore the expectation of lambda t hat plus summation I in S, expectation of theta I hat, Pt IS is also greater or equal than summation I in S, Ri Pt. The interesting part of the proof is showing that the change in the primal is a constant approximation to the change in the dual. Let's do that. All right, so y delta, actually basically y primal objective is an approximation to one objective. So let me define two random variables. So the first, so I'm at time t, you are at time t. I look at the delta primal at time t. This is how much the primal random variable changes. So the objective of the primal changes when the inventory balancing returns the set ST and the consumer comes and picks the item IT. Okay, so delta primal at time t will be equal to R of IT. So IT was the notation that we use for the product that is picked by the consumer. So it will be equal to R of IT, right? As easy as that. So IT is a random variable. It's the product that is picked eventually by the consumer. So now what is the delta dual? So delta dual, and I really mean delta dual hat, not the actual dual assignment, which is in expectation. So delta dual hat, which is a random variable at time t, how much does that change? So lambda t starts from 0, lambda t hat starts from 0, goes to this one. the first term is going to be the summation I in ST Ri 1 minus G of Y T divided by Ci, right? What about theta? What about basic the other side of this is I'm looking at the summation of lambda t, so only lambda t at that time changes, so this is going to be a change. The other part of the objective of the dual is this thing, summation. So it was summation Ci, theta I. And we know that the theta IT is the only one that changes. Therefore, the objective is going to change by how much? By basically C of IT times the change in the corresponding theta, which is R of IT times G of Y IT at time t plus 1 divided by CIT. We can use t plus 1 here, but it doesn't matter really. G of YIT and t divided by CI. All right.
For the first term, why you don't multiply by the selection probability?
You are absolutely right that I have to do that. Thank you. Okay, so now let's try to take an expectation.
Where did that CIT come from?
So in the dual objective, you have summation of CI, right? Right, so I want to look at expectation of delta dual hat at time t condition on history up to time t minus 1. So taking all this as a martingale, so I'm conditioning on the history. There is some randomness at time t. I'm taking expectation over that randomness. Right? So this term has no randomness in it at time t. It only uses YIT, which condition on the past is actually deterministic quantity. So you get basically the same thing for this quantity. What about this one? So what are the randomness in time t? The selection of the assortment. And okay, so basically if I condition on the consumption levels, inventory balancing is maximizing something. It deterministically gives you a particular set. But then there is a randomness which comes from the choice of the consumer. So if you take expectation, then you have to average the behavior of the consumer. Therefore, this term becomes essentially sum over I in ST, right? So you have now, so the first thing is the probability that I will be IT, which is phi t of I and ST. And then you have CI, RI, and let's write this thing again, YIT plus 1 divided by CI minus G of YIT divided by CI. This one is now I. All right. Yes, Thomas.
Here, your lambda is kind of delayed. Yeah, it is used for the beginning value of y, not as you said, the final value.
Correct. Correct. Yeah. So that I can ensure feasibility here. But I actually think if you use the final value, you should just be good to go. But I might, yeah, you might be fine if you just use the final value. But that doesn't matter. All right. So far is good. Now here's the thing. So this thing, again, this is the convex function that we discussed last. So we assume G is convex. It has this form. I'm looking at 2 points. This is YIT divided by CI. This is YIT plus 1 divided by CI. So their difference is 1 over CI. And then you can say this thing is what? So I will find an upper dual. So this is upper bounded by G prime at this point, yi t plus 1 divided by ci, multiplied by this difference, which is equal to 1 minus ci, 1 over ci. All right. This is good. This cancels. And now you get what? And now everything will be upper bounded by, I'm writing this down, replacing it with G prime. So it's going to be essentially sum over I in ST, Ri. And you have three terms. 1 minus G of yit divided by ci plus G prime of yit plus 1 divided by ci. I'm merging the two terms. And phi. Thank you. Let's try to take an expectation here. So I'm looking at the expectation of delta primal t condition on the history up to time t. So this is again sum I over ST phi t is. All right. And I have a good reason to see the little bit here's explanation. I is t Ri phi t ins. Okay, ins. And this is ins. Okay. Now we see what's happening. So if, for example, I could say this quantity is upper bounded by some constant, then you could say the expectation of change in primal condition in the past is at least 1 over c times the expectation of the change in the dual condition. If this quantity was upper bounded by some constants. Okay. And then you could take another expectation, which says expectation of change in the primal is at least the expectation of change in the dual divided by c. And then you could start adding up these changes from time 1 all the way to time capital T. So if you can show an upper bound on this quantity, then 1 over that upper bound is going to be your approximation factor. It's going to be your competitive ratio. Does it make sense? So our goal is actually showing an upper bound here. So now here's the funny part. So if this was yit rather than yit plus 1, then we know 1 minus g of anything plus g prime of everything, that thing. So basically, this is a constant. If 1 minus g of alpha plus g prime of alpha is always a constant, if g of x is equal to the exponential function. So if g of x is the function that we always have, e to the power x minus 1 divided by e minus 1, then this becomes e over e minus 1. And therefore you get a 1 minus 1 over approximation. But then this is a little bit perturbed. This is not exactly by it, it's by it plus 1 divided by ci. But then we are hoping that the fact that ci is large is going to help you to get rid of this perturbation. And this is why the segment of theory we had some order epsilon if the minimum ci is at least 1 over epsilon. So let's calculate that, and then we're going to switch to the Bayesian adversarial. So again, our favorite practice, but this time on the function g prime. So think about the function g prime. G is exponential function, it is convex. G prime is also an exponential function. It's actually e to the power x divided by e minus 1. So still it has this shape. Now look at the 2 points again. So this is y it divided by ci. This is yit plus 1 divided by ci. So I can say g prime of yit plus 1 divided by ci minus g prime of yit divided by ci is what? So it is at most g double prime at point yit plus 1 divided by ci times 1 over ci. G double prime is a monotone function. It is again of the exponential. So this is at most g double prime at 1 times 1 over epsilon. Why? Because ci is at least, times epsilon, because ci is at least 1 over epsilon. And it's just a constant. G double prime of 1 is like
e to the x over e.
1 over e minus 1. Right? So it's just some positive constant, 1 over e minus 1 times epsilon.
And it's e over e minus.
E over e minus 1. You're right. E over e minus 1 times x. All right. So that means that if I replace g prime with g, you get the same thing, only you lose this constant e over e minus 1 times epsilon. So therefore, from this calculation, I can say 1 minus g of yit divided by ci plus g prime of yit plus 1 divided by ci is at most. First, I replace this quantity by it. That gives me an e over e minus 1 when you merge with these two terms. But then you have to also consider this thing, e over e minus 1 times epsilon. So this is basically the same thing times 1 plus epsilon. And hence you get the result that I have. Do anyone has any questions? Any questions about this one?
I'm just curious how tight is the approximation ratio in general.
Great. So asymptotically, this is optimal. So in the asymptotic regime, we cannot do better than 1 minus 1 over e. In the non-asymptotic regime, the same algorithm for any convex function, including actually just identity as g, is going to be kind of like a greedy algorithm. It's going to be a half approximation. But it is kind of like one of the biggest open problems in this literature that in the small inventory regime, can you do better than half? We don't know. There are some, actually, we know that now, so for a special case of this problem, which is the adverse problem, now we know you can do better than half. There is a very recent result, it's a half plus epsilon approximation using a complicated primal-dual algorithm, not of this category. But beyond that, for example, for assortment, I don't even know if that result can be easily extended to assortment. Maybe it can, I haven't tried.
Did I
Yes.
understand correctly? It's not implementable, right? Because we get ST from that.
Correct. So if you have access to that Oracle, you can implement this online algorithm. For example, if it is MNL, you can do that. The funny part is if you have an approximation algorithm for that Oracle, then the same approximation factor is going to appear here. So it's actually a good exercise that if you have access to an approximate Oracle for the offline assortment problem, let's say an alpha approximation, then by plugging it into this online algorithm, we are going to end up with the alpha times 1 minus 1 over e asymptotic completive ratio.
This is an Oracle efficient algorithm.
It is definitely Oracle efficient. You're using your Oracle in an efficient fashion. Just like make one call to the Oracle each time. But my point was you can actually replace the Oracle with an approximation. Right. So if there is no question, let me switch to the Bayesian version of the problem. I probably won't be able to say everything I want to say about that. But okay, now we think about a different model, which is the same problem, but this time I give you informational, I give you distributional knowledge about future. So here we didn't have any kind of information about future. It was considered to be an adversarial variable. But imagine that you kind of know the distribution of the consumer choices at each. So if you think about this carefully, it should remind you of the profit inequality problem, because in the profit inequality problem was kind of like the scenario that at each time there was a value realized from a certain distribution, and as the online algorithm, you knew this distribution. Now we are kind of thinking about the profit inequality framework, but in the context of assortment. And let me formalize that problem. All right, so Bayesian online assortment. Okay, so what we're going to do is the following. Again, we have, let's say, n products. This time, I want to actually change even the revenue of the items or prices of the items over time. So I'm going to define something I call the consumer type, which we denote by tau. So what does the consumer type encode? So given the type of the consumer, let's say type 1, type 2, type 3, type 4, yes.
And why didn't you know the choices from the beginning, even though it could be an adversary instance of choices over time? But I think we assume we know them.
I mean, we get to see the choice at the time that the consumer arrives, but we don't know the consumer choices in the future.
But does it matter?
It matters.
Wow.
In the LP, for example, you needed to know all the consumer choices in order to solve the problem. The online algorithm does is your question? This is the online algorithm, right? So the online algorithm definitely doesn't need to know the future consumer choices. But we were competing against a benchmark that could only work if the benchmark knew the sequence of consumer choices. So definitely the online algorithm doesn't need to know that.
Yeah, but you mean our benchmark needed to know?
Yeah. And we could still be competitive with respect to that benchmark that has a lot of more information than you have.
So that's
What is your question?
because you said we don't know the adversarial selection of the choices, but our benchmark does know.
Right. And they are still competitive.
Yeah, so it's
So now we are going to do way better than that. So now imagine that the input instance is not adversarial. It's realized from some distribution. And I tell you about that distribution. Actually, as we will see, hopefully, you can get 1 minus epsilon approximation of the best algorithm in this case. Not only a constant, you can do way better. In the large inventory regime. And in the small inventory regime, we're gonna be half competitive against, but against a benchmark which is a little bit stronger because the benchmark, well, no, the benchmark is kind of the same. So in the small inventory regime, essentially this distribution knowledge is not going to give you that much advantage, but in the large inventory regime, you can get one minus epsilon approximation, near optimal. But let me define the model. I think the most important part of all this model is actually the model itself. So you have a consumer type, and the type encodes 2 things. So if a consumer of type tau arrives, then the consumer has a choice function, a choice model phi of this time tau of INX. So it depends on the type of the consumer. And this time I allowed the price of different products to be type dependent. So I, the price of product I, last time was fixed. Now it can be a function of time. All right. And then a stochastic type sequence arrives. let's call that tau 1, tau 2, all the way to tau t. What do you know about this type sequence? So the online algorithm knows that type at time t is realized from some given distribution ft. And imagine there is a space of possible types. This distribution has that space as its support. So you know these distributions. You know that the type at time t is going to be realized from the distribution. The rest of the problem is as before. So each product I has inventory, initial inventory. CI, and the goal is to maximize the total revenue. Display sequence of assortments, S1 to ST, and you're going to create in an online fashion that maximizes expected revenue. Total expected. As I said, the problem seems very similar to profit inequality in some sense, because in the profit inequality problem that we saw in the previous class, you know these distributions, rather than types, values are realized. And imagine a special case where you have one product, just like one single product, these consumers arrive, each one has a certain value and the property of choosing that item. And you know the distributions over the types. So this is more or less similar to the profit inequality problem. And in fact, profit inequality problem is a special case.
So you mentioned the price is also not a decision variable.
Yeah, so it's not a decision variable, but it can be type dependent. So the decision variables are still assortments. But this time, if you have when you get to time t, you get to see the consumer type. But then the prices can also depend on that type. Previously, the prices were fixed over time, but this time the prices can change over time.
What does it gain us if we can't do price differentiation? How does it help us then?
I mean,
It's not a decision.
we know the arrival distribution of the future types. And that gives us some information about our decision making at the current time. So you can manage your inventory in a smarter way in some sense. Does it make sense?
Yeah, our future objective essentially we get a better hold of.
Yeah, so these distributions, these F1 to FT, they are all given to you. So this is now your information at the beginning. Similar to the property like when you know the, and you know their order. So basically you know exactly how the sequence is going to be generated, the sequence of types. You just don't know the type realization. All right. So now you can do some funny stuff. The first thing is similar to before. You can write down an expected LP for this problem. And now you can actually solve it offline because you know these distributions. So if you write down an expected LP, basically the expected revenue of a policy that only respects the inventory concentration expectation, you can actually solve that offline with enough amount of computation. And once you solve that, you can probably actually use the solution to design an algorithm. And this is exactly what we're going to do. So let's actually write down the expected LP. And then we are going to talk about the concept of simulation, expected LP. So this time you have to use the distributions. Let me write it down. If you remember the previous class again, where we were thinking about the example relaxation in the profit inequality problem, you saw that in the exam, you saw that in class. This is the same object, but the extension to the assortment optimization. Let me try to write it down. So we are all these. So we are maximizing. What is our decision variable? At each time t, given type tau, but you get to see the type. So at each time t given type tau, you want to put a fraction on every subset. So you have x of t, tau, and s. All right. So now, what are we going to do? So we are maximizing sum over t from 1 to capital T, sum over all subsets, sum over all items in that set. All right. Now, let me write it down in language of expectation because it's just easier. Expectation of tau is realized from the corresponding distribution time t. And given a specific realization of the tau, you're going to assort set S with this probability, x, t, tau, and S. And then the consumer comes, it's item I with probability phi of tau, I, and S. And then you get the revenue, which is equal to R, I, tau. And this expectation is essentially another summation, but I write it in language of expectation because it's just easier. It's a linear function, subject to, all right? So at every time t, no matter what type is realized, you want to have a distribution over x. Therefore, summation of x, t, tau, s over all subsets should be at most 1, and x, t, tau, s should be greater than 0. What else do we need? So we need to satisfy the inventory constraints and expectations. So you want to guarantee that these probabilities are chosen in a way that the expected number of units that you sell from each product is at most CI. How to write that constraint? So kind of like similar to before for every I. So if I decide the sum T over T, and then I take a summation over all the sets that contain item I, and then I look at the expectation tau realized from FT, the probability that I assort the set, and I multiply that by the probability that the consumer picks the item I from this set now. Then this should be at most 0. Right? Okay, so as we say, I can write down this LP at time 0. And I can actually solve it. I'm not going to work with dual, but to kind of answer your question, Chen, in order to solve this LP has exponential many variables and polynomial many constraints. If you look at the dual, similar to before, that the separation oracle was really solving an assortment optimization problem. The separation oracle for this LP is going to be an assortment optimization problem. So exercise. Show given access to an algorithm for solving offline assortment. The dual of the expected LP can be solved efficiently and hence the primal. If you don't know how to solve the linear program with exponential many constraint given a separation oracle, come to me after the class. I would be happy to send you some pointers. And also, if you can solve the dual using separation oracle, there is a way to solve the primal. Again, I would be happy to point you out to some references for this. Yes, Mark.
Is this our benchmark for online?
This is gonna be exactly. So this is playing the role of benchmark on the Clairvoyant optimum. Basically, any online algorithm which you can think of, its expected revenue is going to be upper bounded by this one. And again, this is the second exercise. The proof is exactly similar to before. Show the lemma. What is the lemma says? That says that if I look at this opt LP, expected revenue of any algorithm is at most the expected object. This is again easy, just like think about any online policy, replace its choices with indicator random variables, then write down the same linear program, replacing these expectations with indicators. Then because you have feasibility points-wise, it's going to be feasible in that version of this linear program, then you take expectation from the constraints and the objective, and that gives you the full proof. But this is really at the level of an exercise. If you want to train your online optimization muscles, I think these are the type of things that you might want to think about after. Yes, ma'am.
Would the solution to that be anticipatory?
Anticipatory.
Because if it is not, then
Yeah.
you can run it online and then.
You can solve this, and then you can run it off online. You're absolutely right. I can solve this. Gives me x star t tau s for any t for any tau or any s. And imagine that I have exponentially numbers now, but suppose that somehow magically you can sample from this thing. So then you can design an online algorithm that samples from this distribution. But it's not going to be satisfying your constraint point. It's only satisfying the expectation. And let's actually do that. So Mohammed's suggestion is I solve this LP. Let's pick a name for this thing. So we call that the simulation-based algorithm. Simulation-based algorithm. How does it work? Very simple. At time 0, solve expected LP. And for now, imagine that I have infinite amount of computations. Don't worry about the computational issues. There's a workaround around it. But for now, imagine that computation is not an issue. So that gives me the optimum solution, x star t tau s. Basically, it says that every time t, if you get to see the type tau, here is the distribution of sets that you have to sample. Okay, and we know that they are distributions in some sense. All right, good. So now, here is the online part. At each time t, sample the set st from, okay, at each time t, observe the type at this time. Let's call it tau of t. So the consumer arrives, you get to see her type, the feature vector, or any kind of contextual information you have about the consumer. Now, sample a set S from the distribution x star t, tau of t, and s. And here, let's call it S. And here, note that in fact, in the optimum solution, this constant is going to be typed. Note that x star t, tau t, and s is always greater or equal than 0. And the summation of this thing over all the sets, t, tau, t, s, is exactly equal to 1. So this is defining a distribution over subsets. You sample from the distribution and display that to the consumer. All right. Seems to be really great. What is interesting about the simulation-based algorithm, if you ignore the inventory constraints, let's say ignore the fact that I have limited number of each product.
How is it one?
What's that?
How is it one?
In the optimum solution, this constraint is going to be tight. But if it was, I mean, you don't need to even think about that. Suppose it is not equal to it's at most 1, that means with the remaining probability, just don't display anything. Without the subgenetic assembly. So now, if you ignore the inventory constraints and you just sample these sets, then in expectation, the revenue that you can get is exactly equal to the objective function of the expected LP. But that's not the only guarantee it has. In fact, you satisfy the inventory constraints in expectation, meaning that if I look at the particular product I, and I look at how many number of that item has been sold in the simulation-based algorithm, this is a random variable, but then in expectation is exactly at most CI because of these constraints, right? Let me write these two things. Claim 1, expected revenue of simulation-based SMB. Expected revenue of SMB is exactly equal to opt-LP. You're ignoring the constraints here. Claim number 2. If I define y I capital T to be the final consumption level of product I, basically the number of items of this product that are going to be sold in the entire horizon, then the expectation of YIT is going to be at most CI. Right? Yes.
For example, did you use some epsilon from CI, solve that for that LP and use some concentration?
Yeah. This is one way to get 1 minus epsilon approximation. Under a very important caveat that I'm not going to get to, because if I get time, I'm going to get to that. It's related to that sub-assortment dampening at the end. But Mohammed Raja's suggestion is the following. Imagine these CIs are large numbers. Let's say I multiply the CI by some 1 minus epsilon at the beginning to give myself a little bit of slack. I solve this new LP at the beginning and sample from that. So now I know the number of items that I'm selling in expectation is at most CI times 1 minus epsilon. And then when you think about this, at each time you have an independent stochastic process. You have an independent selection. Everything across time is independent. So then when I look at the YIT, by a capital T for one product I, it's the summation of a bunch of Bernoulli random variables that are all independent with certain marginal probabilities. They are equal to YIT. Their summation in expectation is CI times 1 minus epsilon. Now you can use a concentration bound, a Chernoff bound, to say the probability that the summation go above CI is going to be very small if epsilon is, for example, in the order of 1 over square root CI. Yeah.
Even if you don't subtract, that's still the same thing.
No, so it's a symmetric distribution. So probably half it's going to be above CI. Yeah. So you need to give yourself a little bit of a slack. If you don't give a slack, then it's going to be just a constant probability. It's not going to be almost 1. Imagine I have a bunch of Bernoulli random variables. So the sum of their probability is equal to C. If I start realizing my number actually might be greater than C, there are anti-concentration bounds actually that give you constant probability for this. the large deviation down.
Yeah, but the deviation becomes smaller and smaller. The deviation will be square root of t.
Right.
Yeah, if you
And that's the slack that I'm talking about, right? So basically, so I mean, your point is well taken. I guess you're saying if I don't change and I look at the actual number I get, eventually it's going to be CI plus a square root CI.
Yeah.
Right.
Yeah.
But this is not feasible. So if you cut it at CI, then
you're losing something from BNP, but you don't know how much.
But that would be square root of CI.
But no, because the distributions change over time.
Yeah.
So you are not sure from which part actually you lost that square root CI. You're right. I mean, your actual idea is correct. But
Okay. So if the distribution would be ID.
yeah, then what you said is completely fine. So I could just like remove the slack, solve it as it is, and stop the moment that I violate one of the constraints, and that should have been fine.
Also, the worry is that the sample is set to show any of that items could be missing because you have run out of inventory. Now, if you take a union bound that, oh, am I missing? None of them, right? Like intersection of not missing any of them, and that could still be a large probability event. Like, what do you should do if an item S set is missing one item and you want to show it? If you show a different set, then there's a very different choice problem.
I mean, that
No, actually here we are not going to use union maps. Basically, if there is an unavailable item, you don't put it in your set.
But then choice probabilities have changed. Right? So you're showing a different set.
There is this process, there's a procedure I haven't revealed yet called sub-assortment sampling, meaning that you have a target set.
Right.
And I give you some probabilities that are smaller than the choice. So this will give you a joint distribution over subsets that matches exactly that probability.
I see.
So it corrects for the effect that you have.
So here we want to show we only lose square roots of the items.
But I guess maybe, yeah, so I mean, we can talk about it.
But with this, I think what Chen is saying works. But you need to correct for this.
So you basically keep track of xt, tau, I. So that's the
Yeah.
probability with which I somehow want I to be sold, and you can online decide the distribution over sets to somehow do that. That's what it's
Exactly. All right.
But like, how does it work in practice? Like once you, I mean, so far since you've not revealed that thing, this can hit with some probability at least. A situation where it cannot choose the set. And then what does it do? Like rejection sampling kind of thing? What does it do? Keep sampling again and again till it gets a set.
So if you hit the capacity for a product, just don't use it in your assortment. This is relevant to the conversation we just had, right? So how to run this algorithm in practice, like the version that Mohammed has mentioned. So you can diffuse the capacity.
Yeah, with Slack.
With a
even with
Slack and then start simulating. So
Even
version
with-
number one, the moment that you run out of stock for one product, just stop. That's version number one. Version number two, which is actually the version I suggest, is if for one product, you hit the capacity, continue sampling, but if your samples that had that particular product, do not include that in your samples. But then the worry is, because you're now looking at a smaller set, then the choice probabilities will be different. There is a way to correct for that. I probably won't have time to show how to do this. It's actually a recursive function that will give you this distribution. It's kind of like cute. I'll send you pointers to where you can find the proof of this fact. In the remaining time I have, I will just switch to a different way of thinking about this problem and talk about online contention resolution schemes. How it will be connected to making the simulation-based algorithm points-wise feasible. I'll send you some pointers. Let me talk about online contention resolution because I think it is interesting by itself. So the idea is, in this problem, when you start simulating, imagine that I'm assigning a separate procedure to each product. So the goal of that procedure is to maintain the feasibility for that product. Meaning that the goal of that procedure for that product is to make sure the total number of items that will be sold from the product is at most. And I will have parallel procedures, one for each product. So the simulation-based algorithm starts simulating, and these procedures finalize the choice. meaning that the simulation-based algorithm suggests the sets, but you are not going to put everything in that set. You should ask those procedures that, hey, simulation says that product I should be displayed to the consumer. Do you finalize this selection or not? If the procedure says yes, then you're going to put it in the set. If the procedure says no, then you just ignore and go with the remaining items that have been selected, have been suggested by the simulation design. Now, from the perspective of that procedure, the one that is sitting on some item, you get requests for, hey, this item should go in the set, this item should, you get binary requests. And somehow you know that, well, so these Bernoulli randomers, these requests, think of them as randomers, these Bernoulli randomers, some of their expectations is at most CI. But you're only allowed to pick CI number of them, because you want to maintain the feasibility points-wise, not only an expectation. Okay? So the question is the following. What is the optimal procedure you can run for product I so that you guarantee the minimum probability that you accept the request is high enough, and at the same time, the total number of requests that you accept is at most CI. Okay? So let me formulate this problem. It's called online contention resolution. It goes by the name of the magician problem as well, but I'm going to go with the OCR. So what is the problem? There are n boxes. Each box has a Bernoulli random variable with probability Qi. So you know that the summation, I'm just looking at a special case where Ci is equal to 1. So you look at the summation of Qi, I from 1 to n is equal to 1. And then an online algorithm gets to see these boxes one by one. So you're at time 1, you decide whether to skip this box or stay at that box. Then the Bernoulli random will be realized. If the Bernoulli is 1, if the box is active and you decided to stay, then you're going to stop. If the box is inactive, you decided to stay, you're going to go to the next round. If you decided to skip, by default, you go to the next round no matter whether the box is active. Okay, so for rounds T from 1 to n, there's an algorithm that makes a decision. So the decision is either a stay or a skip. So now, at this point, the box at time t is open, meaning that you get to see whether, let's call these random variables, so let's call them BI, for example. So you get to see whether BI is 0 or 1. If you decided to skip, you just go to next time, no matter what the outcome is. If you decided to stay, if BI is equal to 1, game ends, and you stop at time t. If BI is equal to 0 and you decided to stay, then you go to next time, next round. So in fact, so you are observing a bunch of elements that is some probability are active or inactive. If you look at the sample path and count how many number of active elements you have, in expectation you have 1. But your goal is to only pick 1 exactly as you get to see these active, inactive statuses in an online fashion. But at the same time, what you want to guarantee? You want to guarantee that for any time t, you want to design an algorithm here such that for every time t, so this is the goal, the probability that stops at t condition on bt to be equal to 1, you want this probability to be greater or equal than some constant c, and you want to, so basically your goal is maximize c. So you want to be as uniform as possible in some sense. So you want to be fair. For example, imagine that you say, okay, I'm gonna pick the first box that is active. So basically, I'm gonna stay every time. If you say I'm gonna stay every time, then you're giving more advantage to the earlier boxes and less advantage to the later boxes, right? So then, if there is a box that is active at the end, then it's really likely that you won't get to see that box. But if there is a box that is active at the beginning, you're gonna probably see this box, right? But as you see, here the goal is kind of like guaranteeing that no matter where the box is, condition the box being active, you pick it with some probability, or you get to see that box with some probability. If you remember from the previous class, this is very similar to one of the methods that we learned in order to solve the profit inequality problem. Just refresh your mind, here is a simple algorithm that guarantees C equal to 1/4. So imagine that I'm the algorithm. So at each time I flip a random coin, unbiased coin with probability half, independently across time. So if the coin is 1, I'm gonna stay. If the coin is 0, I'm gonna skip. Okay. So I guarantee that, well, so because the summation QI is equal to 1, then it's probability at least half. I'm not stopping until any time t.
So it guaranteed a sort of exploration, and then the fact that you explored everything made sure that you could actually match the objective of the sum constant. I think that was the idea.
Right. So basically, if I flip this coin, let's say I'm at some time t. If all of the previous coin flips are skip, then basically, what is the worst case scenario? The worst case scenario is that all of my coin flips in the past are a stay. Even if I say a stay in all the previous times, then what is the probability that I see today?
2 to the minus m times product of 1 minus fi.
Basically, what I'm trying to say is that if you have no, let's calculate it. If you have no a stay in the past, then definitely you're gonna see this time, right? And using union bounds, what is the probability of this event? I claim it is at least 1 minus half times the summation of QI in the past. Right, because at each time you flip a coin, if you decide to stay, with probability Q, you are going to stay. With probability QI, 1 minus QI, you're going to see the next time. So then you can say, well, so the probability that I skip at any time is at most the probability that I skip at time 1 plus the probability that I skip at time 2, so on and so forth. And then each of these probabilities is at most half times the corresponding Q because you're flipping a coin, right? That means that the probability at least one minus half time summation of Q t prime for t prime is smaller than t, I get to see time t prime, right? But here's the thing. You want the algorithm to stop. And at this point, and by the way, so this probability is at least half, because summation of q's even until the end is at most 1, is actually equal to 1. So this quantity is at most 1, and therefore this is at least half. But then here is a catch. So even if I haven't stopped up to time t, I'm not going to stop at time t unless my coin flips correctly, which happens with another probability half. So therefore, the probability, so we probability at least is, you get to see t and then you can say with probability at least this quantity, which is the probability that you get to see time t, times the probability that you decide to stay at this time, which is 1/4, you stop at. So just to make sure what is this algorithm. So the algorithm, flip a coin, half. If the coin is 1, then stay, otherwise escape. Okay. So this basically simply gives you like a 1/4 probability for this problem. But actually, with linear programming, you can find the optimal solution. You can show the best quantity you can get there is half. Let me do that. And then I think I'm gonna end the course. I'm gonna send you some references on how to use these online contention resolution schemes together with the simulation-based algorithm in order to have first a half approximation for even ci equal to 1, and how to get a 1 minus 1 over a square root ci, basically 1 minus 1 over a square root c plus 3 approximation for general c. So if you use concentration bound, the best thing you can get is 1 minus log, square root log c divided by c. This is similar to what you got in the final exam in the last quarter. You can get rid of that log c by solving a linear program similar to the one that I'm solving here, but for general C. And this is a very beautiful paper. I will send you pointers to that. This can be one of the topics that if someone wants to define a mini project around would be an interesting subject. Okay, so I have like 5, maybe, can I use like 5 extra minutes? Like if you give me 10 minutes, I can show you how to design an algorithm that is a half approximation. All right, so let's think about this. An algorithm can be described by basically 2 sets of numbers. So what is the first number? So the first number is the probability that you get to see sometime. Like for example, for that algorithm, probability you get to see any time was at least half. So you define a state variable, st, which is the probability that the algorithm does not stop before t. Okay. And then the second one is the probability that xt is basically the probability that algorithm decides to stay at time. Okay. Now, let me write down a linear program. So I'm trying to maximize C such that, first of all, I want xt to be at least C for any t. Because if I can guarantee that my algorithm is going to stay at every time it's called C, that means condition on that time being active, you're going to stop at that time. With probability C. So this event that you decide to stay at T is basically and of two events. The probability that you have reached T